not in standard, that is not in graphing form and get it kind of there. If you kind of follow, that's the idea that we're going to be working on. So today, I think the idea that I have is that we're going to be looking at the following. So give me one more moment. Who's coming in? Can't tell. It must be Daniel Hilaire. All right. So anyway, so off we go. Let's see what we can do here. So let me give you a little something right off the bat. See if you guys can remember how to do something. So here we go. That's the course you're in. So can you guys try to rewrite those two in more of a standard form, those first two, and do a little bit of factoring back from algebra 2 times and see if you can handle that. So, oh, can you guys online see that okay?
Yeah, it looks great.
Okay, perfect. So first one should be pretty dang easy. Should be pretty simple little set of answers for those first two, and for 3 through 5, that should be pretty simple little factors. Does that look a little small to you guys, those exponents? Yeah, sorry about that. For some, when it's in shared screen, it shrinks everything down a little extra. So that's a number 3 is x cubed minus 16x. And number 4 is x cubed plus x squared. So we'll kind of talk our way through some of those in case you're having a little bit of difficulty. So what do you guys notice about number 1? If you divided everything by x, what would happen? Yeah.
What do you go down power? What are the powers of number 3?
Number 3, it's x to the third minus 16x.
Number 2.
Number 2 is 2x to the fifth minus 8x to the third plus x squared over 2x squared. I wish there was a way that I could change that resolution if I'm in shared mode, but I just don't think the way the share screen works for DL doesn't work well with PowerPoint if I don't have it mirrored right now, and so that's why I'm doing that. So sorry that it looks a little small for you guys. Could somebody help me out with number 1? How does that simplify out? What happens when 2x cubed gets divided by x? 2x squared. And then what's the next piece? Plus 3x, and then plus 1, right? So the point being is that if you're going to divide by something, you got to be fair and divide every single piece. So in number 2, you would get x to the, I know it's a little small, but you should get x to the third, then minus minus 4x. And then the last part, what happens when you add x squared and you divide it by 2x squared? You just get a half. That's it. So we should have x to the third minus 4x plus a half. And that's it. All right, you guys notice anything nice about number 3? What's the GCF? Just an x. That would leave you with x squared minus 16, but that's one of those nice easy ones. What's x squared minus 16? X squared minus 16, that's one of those nice easy ones. X plus and minus 4, you got it. Now number 4 was a kind of a new introduction that I gave you guys at the end of when I saw you guys. It seems like a long time ago now, but it was last week. Was that Tuesday that I saw you guys last, or was it Wednesday? I guess it doesn't even matter anymore, but it was a long time ago. But you guys remember the little trick that I gave you on that one? So I think I'm probably going to write that and share it a different way, because I have a sneaking suspicion that you guys may not remember that, since it was kind of new. last time. So let's see if I can make that nice and big and bold for you. Is that maybe a little bit better? I don't know. But I gave you a hint. What happens if you have specifically 4 terms? Do you guys remember the little trick that I showed you last time? It was called factoring by groups or grouping. What do these two dudes right here have in common? They both have an x squared. And if I factored out that x squared, what would they have left? They'd have an x plus 1. And then over here, what you're hoping is that you still have that x plus 1 in the second set of groups. What number needs to go in front to make it true so that this times this x plus 1 retains this information right here would be a 4. Now, if I'm correct, what do these two groups have in common now? They have an x plus 1, and if I factor that out, what is left after I take out the x plus 1 out of both of those? An x squared minus 4, and yet again, what do you notice? Just like the previous problem, we had x squared minus 16, this is x squared minus 4, a really nice, easy problem. What is x squared minus 4? Plus and minus 2. Now, one thing that I would love to see you do when you're doing problems like this, especially coming up, you know, when you have an exam, and I know it's going to be a good while before we have a test, again, since we just had one, but I would love to see you take your original problem, make it y1, to make your factors y2, and what should I see? You know, the graph can be deceptive because sometimes one of them fits on the graph and the other does not fit on the graph. I hope you can see that I typed all that in right there. So one of the things that I kind of like to do is I just like to look over at the table. And I hope you can see that on the table, what do you notice about my table values for my two functions? They're perfectly the same no matter what, which means, you know, if I had done something silly and I'd made a little bit of a mistake, I want to be really clear that if I had made a mistake, do those tables look the same now? So you can tell it's not just like, oh, hey, what do you know? They're the same no matter what. No, they're not. They're only the same if you did the problem correctly. So we had a couple of problems that were in standard form. We got them into the factored form pretty easily, didn't we? Those are pretty nice, but they're not always nice. So we had, let me see, let's go back to this. So we started last week just discussing a little bit of long division. So let's see if we can remember how to do some long division. Now, the question is x minus 3 in fact a factor of that? Does it divide in perfectly? Because honestly, on this particular problem, if I did a factoring by grouping, I can promise you it would fail. See, even though it has 4 terms, one of the things that I was trying to show you last week is that I put a question mark, like, I wonder, does it work? This one is a big fat no, it does not work. So I'm just guessing, does x minus 3 work? So if you recall, what do we start with on the long division? This thing kind of sucks. What do we need to multiply by x to get 2x cubed right here? It needs to be a 2x squared. So I'm going to pop a 2x squared up in that hole right here. Now, I guess I'm going to have to kind of go the other way because I thought I put it in, but I think what I discovered when I tried to do this problem myself is that animating the whole thing in here was, well, not going to happen. So anyway, we had x squared, right? Actually, it was 2x squared. So we had 2x cubed, we had a minus 6x squared. So what's the next step of my story? One that a lot of people really struggle with, it feels weird, is you're supposed to subtract, right? In division, you write that number and then you subtract. But back in Algebra 1, my teacher always told me never to subtract. He said add negatives, which I thought he was a jerk at the time, but I kind of understand the point is that when you get into some of these problems, you want to change all the signs. So Hez, what do I need to get to 2x squared? $2x, you got it. I'm going to put the 2x right here lined up with the 8x. That would give me 2x squared. I would get negative 6x, and then what do we do? Change the signs. And then we come down and we got 14x minus 2. So what do we need now? I think we need a 14 right there. Now, by the way, the good news is when you get to that number 14, what does it tell you? I'm kind of done. There's nothing more that I can do. There's no more room. So if there is anything left, what are we going to call that? We're going to call that the remainder. And we're going to get 14x minus 42. We change our signs and add, and we got 40. And so we used to write R40, right? It's so dorky that we used to write it that way. So anyway, that should be pretty simple conceptually, which is why you see what you see right there. So I want to see if you guys can do that one right there. You've got 2x to the fourth plus x cubed minus 3. You're going to divide that by x squared plus x plus 1. Now I want you to notice something. You got 2x to the fourth plus x cubed minus 3. Do you notice anything that is troubling? There is no x squared term. What else is missing? The x term. So you need to put it in. Just put in a 0x squared, put in a 0x, and then you're going to be good to go. So I'm going to let you try for a second. I do have an answer that I'll pull up in 1 second. Make sure that you guys can do that. And then we're going to start talking about some nice ways that we can jump out of that thing fairly quickly. All right, Cooper, what's magic? What do I need for 2x to the fourth? 2x squared. Put it right there. So I got a 2x to the fourth. I've got a 2x to the third. I've got a 2x squared. D, what do we have to do after we do all that? Flip the sign. Boom, boom, boom. Pop it on down. I'm going to get negative x cubed and negative 2x squared. I don't have any x's. Okay. Next up, Nico, what do I need to get a negative x cubed out of this thing? Negative x it is. So I got a negative x cubed. I've got a negative x squared. I got a negative x. Then we pop our signs. What's going to happen when we come on down, Dakota? What do we have down here?
Minus x squared plus.
Wait. Was that, did I write that down wrong? Was it a 3? Okay, should be a minus 3, I think. It's all good. Now, Devin, what's left? What's our last term? Just a negative 1, and so we got our negative x squared. I got a negative x. I got a negative 1. We flip all of our signs. So did it go in perfectly? Why not? Because it has a remainder, doesn't it? It's a 2x and a -2. So what we could write it as is we could write r, but a smarter way is to write it as 2x minus 2 over all of this stuff. So one way to know that you're done is if your remainder has a lower power than the original divisor, or if you line it up when you're out of room, you can kind of tell. You see that? Now, do you guys like that version? Do you guys like the long division story? I think most of you would probably argue, you're like, yeah, not a huge fan of that, right? So I think this is going to be a blast from the past that you guys will have done last year. We're going to see. I think you have done this before, and it's called synthetic division. So do you guys remember hearing about synthetic division? At least modestly so. So if someone said, hey, I want to take x to the 4th minus 3x to the 3rd plus x squared minus 2. And did you guys notice that I left something out in there? And I wanted to find out if x minus 2 is a factor. So the question is, can this be factored where x minus 2 is in fact one of the pretty little guys that sits in there? So what you do is you look at the denominator. What would be the root of that denominator? What's the value that would make the denominator go to 0? It would be the number 2. So this is my way of doing this. Your Algebra 2 teacher may have done it symbolically a little bit different, but it's going to be the same concept. So I start off with the root of the denominator right here. Then I just go ahead and I skip in and I write all of my coefficients. Now, this is very much like what we did when we dealt with matrices, if you recall. You lined it all up, and what do you know about this one right here is that actually stands for 1x to the 4th, doesn't it? That stands for negative 3x to the 3rd. It stands for 1x squared, all the way down the line. Now, what we're going to do is we're going to pop that 1 straight on down. Do you guys remember doing this a little bit? And then you would take 2 times 1. What's 2 times 1? 2. You add down, you get minus 1. You guys remember doing this, I think? I hope so. What's going to go right here? 2 times negative 1 is going to be negative 2. You add down. You multiply, you get that. So you go down the line, and this is what I've got. Now, that just looks like a whole bunch of numbers, and I get it. But what those numbers represent, what happens if you take an x to the 4th and you divide it by an x? What is x to the 4th over x is an x to the 3rd. This is meaning the answer is x to the 3rd minus x squared minus x minus 2. And there is my remainder sitting right there. Now, was that a little bit nicer than long division? Now, the question is, like, why does that actually work? Because there's some things that weren't there that we did before. But one thing that's really nice is, what would it take to make x turn into x to the 4th is x cubed, isn't it? You can kind of see it right there. The one piece that's missing that sometimes freaks students out a little bit is, what is the big piece that I was trying to really emphasize by changing colors every pick and time in that other? Notice that change of signs? Did I do that here? Where did I do it? Did I actually change the signs up top? Did I do that in this problem? See, I wrote the numbers down. I multiplied, I added, did I ever change the signs? Yes. What did I write down? I wrote down a positive 2, not a negative 2. Did I change the sign? So every single time when I multiplied, Did I actually multiply and simultaneously change the sign? Shut out. Okay, so a little shortcut. You like it? Isn't that kind of cool? So that's kind of my way of doing it. Now, here's the downside to that. And math has a lot of these little cool shortcuts that work some of the time. So why would I take you through all the pain of doing long division if there's this shortcut? Why would we do that? Doesn't that seem mean? Well, what would you divide by right here? See, I love synthetic division. I think it's phenomenal, but we have a problem, everybody. The problem is, when does synthetic division actually work? Synthetic division only works if f of x is being divided by x minus c. Now, as I say that, that's going to seem a little bit strange to you guys, but I want you to notice something. What is my leading coefficient on this x minus c? 1. Which means technically if somebody says, hey, let's divide by 2x minus 3, then it doesn't work anymore. What if somebody says, hey, let's divide by x squared? I'm out. Can't do it. So synthetic division is fantastic as long as you have a very, very, very simple denominator. Do you follow me? It only works in the simplest of cases. When does long division work? All the time. So that's the pro and the con. But how much do you guys like this in comparison? Kind of a lot better, isn't it? So here's what I'm going to say is, if you're going to look at all of those things, I would honestly tell you we're going to try to fight really hard to see if we can work on it. So going back in time, if I told you that I wanted you to take like 240 divided by 15, most of you probably don't know what 240 over 15 is, do you? But a lot of you probably recognize that the top and bottom are both divisible by 3, don't you? And you could go like, oh, 80 over 5. Could you? And then you go, oh, and 5 goes into 80. That's no big deal. That's 16. I didn't know that 15 times 16 was 240, but I could do it in stages, couldn't I? So what I wanted to do is show you a problem that is my way of kind of faking out the story ever so slightly, because sometimes we have really nice stuff and sometimes we don't. So I'm going to try to keep it fairly gentle here. I'm going to go with 2x to the third minus 8x squared plus 4x minus 3. And I want to try to divide that by 2x squared minus 5x minus 3. Now, what I can tell you right now is technically by the rule, I cannot use synthetic division on this problem any longer. You guys understand why? Because it just technically is not in the rules. But if I wanted to, I could just go ahead. I'm just going to draw a squiggle because I don't feel like drawing all that out. But if I factored it, and I kind of rigged this problem off to the side to be this right here. So although I can't divide by that, could I, just like in this previous little tiny silly example, could I divide in phases? What is the thing here that I could very easily divide by? I could divide by 3, couldn't I? Well, that's not too bad. So what goes in the little hole up here on the top? It's just going to be the number 3. And I'm going to go with 2, -8, 4, -3. Now, is it possible that this 3 could go in perfectly? Yeah, it might. It's in the realm of possibility. So we're going to go through the little process that we went through. Oh, and just for a little smidgen of a second, I thought I was going to get lucky and it was going to work, but it didn't. So what does this thing stand for right now? What does this 2 stand for? It stands for 2x squared. Minus 2x and this, and then what is this guy right here? That's my remainder. And here's what I want to do, because I personally am a little obstinate. I really, really, really like synthetic division. So here's what I'm going to do. I'm going to look at that thing and I'm just going to call this negative 1/2. Now, is that the root to the other piece? Okay, well, let's try it. Let's pop that down. What is negative 1/2 of 2? That's going to be minus 1. I pop that down, that's negative 3. Now, some of you guys aren't going to like this very much, but what's going to come next? It's going to be positive 3 over 2. Add down, I get negative 1/2. And then I got positive 1/4, and then I've got, dang, what is negative 9 plus that? It says negative 8 3/4. What is negative 8 3/4 as 35/4? Okay. Now, you might go like, gee, that didn't help me very much, but it actually kind of did. So there's something kind of tricky that just happened. I just replaced this 2x plus 1 with an x plus 1/2. Would this and this be the same thing? Would they have the same root? This right here fits the rule that I gave you, but this didn't fit the rule. So anybody have a guess what I have to do to make it actually correct now? Because I actually divided by this and not what, almost. He said multiply by 2. If I put this 2 out in front, does it now say the same thing as that? Where's the 2? It's in the outside, but more significantly, it's in the denominator, isn't it? That means I'm going to divide all these guys by 2. So I actually have 1x. I have a minus 3, and then what are all of these little pieces right here? All those little pieces are my remainders. And so this one was being divided by 2x plus 1, and this other remainder, which is negative 35, I should have divided by 2. Sorry, I forgot to divide that one by 2. And this last one, when I divide it by 2, it actually has the full 2x plus 1 and the x minus 3. So I know that feels a little bit awkward. Normally, we don't bother to show that summary statement. But if something is not linear, you can get away with it if you do what? Divide it in 2 parts. You notice what I did is I couldn't divide it all at one time, but I could divide it in stages. Hopefully that kind of makes sense to kind of how this is playing out. So what I wanted to do is I gave you guys some notes, and those of you guys that are online, it's not anything huge, it's just helped to write something down. So this is kind of what the ancients did back in the day. But the factor theorem says the following. So keep in mind, our whole goal is to take problems that are very, very, very difficult to handle and turn them into something that's a little bit nicer. So our factor theorem basically says if f of x is some polynomial in standard form, it's a sub n x to the n, a sub n minus 1 x to the n minus 1, all the way down to a sub 0. That's kind of the standard form that we've been doing. This is going to be kind of a strange little idea here, so you kind of have to take it for what it is. Then all the rational zeros. Now, zeros, x-intercepts, roots, those all say the same thing, are of the form P over Q. And I know that you've done this back in Algebra 2, but this is going to feel really, really awkward. It's super hard to kind of adjust all this. Then all of those things are of the form P over Q, where P are factors of a sub 0, and q are factors of a sub n. So I kind of think I wrote that in the wrong spot. That should have been down here under possible rational roots theorem, but that's all right. So let's kind of go through what that means for us. So if we're going to look at this thing and we're going to try to figure that out, what are the numbers, everybody, that can go into the number 8? What are they? 1, 2, 4, 8. Okay, so notice it says P over Q. So I'm going to look at these. These are what I call P. They're 1, 2, 4, and 8. What are the numbers that go into that front number? 1 and 2. Now, what I haven't really mentioned, the fact is those could be positive or they could be negative numbers. So that's kind of a long list. So the possible numbers that could go into that are the following. I usually put a squirrely brace and then I put a plus or minus in front because I'm going to make a list. Now, if I wrote any one of these numbers, 1, 2, 4, and 8, and I divided them by 1, because remember, these are the numerators, these are the denominators. So what happens if I take 1, 2, 4, and 8 and I divide them by 1? What do I get? I get 1, 2, 4, and 8. But what would happen if I divided all of these by 2? What else could I get? I'd get 1/2. I would get 2 halves. But what's 2 halves? 1. What is 4 halves? And then 8 halves is 4. So here's the kind of interesting thing. This is kind of what the ancients figured out. It's like, of the infinite number of answers that are out there that I could guess around and figure about, what have we cut infinity down to? How many? Careful, it's not 5. Should have put a comma on that 4. 10. Because there's a pesky little plus or minus in front of it. Now, have we already established what I could do to find out through synthetic division how to find out if one of them works? Because if they work, what does the remainder have to be? If something goes in perfectly, its remainder has to be 0. Are you guys cool with that? Well, here's the thing, everybody. Do we really want to guess around at 10 ideas? I don't. I don't want to do that. In fact, they didn't want to do that either. So even doing that, that was not enough. We wanted to look for some things that would be helpful. So here's my first hint. I graphed it for you, and I found the following. When I did it on my calculator, it looks like there's some root somewhere between -1 and -2. There's another one between -1 and 0, and there's another one between 1 and 2. So here's the thing. What degree is this polynomial? It's a 4th degree, so how many roots can there be? There can be as many as 4. Oh, and by the way, there's one more. It says it actually hit the axis at precisely x equals 4. So let's see what we can do. So what I will do usually for you is I will allow you a graphing calculator to take a look at it to cheat. Now, did Descartes have a graphing calculator that he could do that? No, but he didn't take 8 classes at a time and all that kind of stuff. We need to go a little quicker, so we need to cheat just a little bit, have a little bit of extra help. So what we're going to do is if it hits the x-axis at 4, can you guys tell me what the factor is that goes with that? What would we be putting in the synthetic division if 4 worked perfectly? It's going to be x minus 4. So I know that somehow when I'm all said and done, g of x is going to have a factor of x minus 4. Now, Just like what I did right here. The first thing that I said when I said 240 over 15, the first thing I did is I just looked for something I knew worked. And I knew that 3 was going to work and make the problem get smaller, correct? Do we know that the number 4 is going to work? So if I could divide that 1 out, what's going to happen to the size of my polynomial? It's going to get smaller. So let's do that. Let's put a 4 right there, and let's make our polynomial get smaller. Now, before I go on, are there any missing terms? Should I have a 0 in there anywhere? I got an x to the 4th, an x to the 3rd, an x squared, an x, and a constant. So I think we're good. And so what do you guys already know better happen right there if I am doing this correctly? It should be 0 because what I'm telling you is it had to go in perfectly. So we're going to do that. 2. That gives me 8, 1, 4, negative 4. Hopefully you can see that synthetic division, you can work that through almost as fast as you can write. Now, what does that represent right now? It was an x to the 4th. I divided it by x minus 4. What power should be left now? This is an x to the 3rd. This is my little cubic that's sitting right here. Now look through here real quick, because there's a bunch of breadcrumbs that I handed you. This is the list of rational zeros. By the way, what am I not listing? Irrational numbers, which, by the way, sorry everybody, I'll never give you a list of irrationals. If you can invent that, welcome to your PhD. You'd have it, because no one has ever been able to figure out a way to list the potential irrationals. All we can do is list the nice ones. That's all we've been able to do for hundreds of years. That's all we got. But look at my list. Is there anything in this list between -1 and -2? Do you see anything in that list that fits? Is there any fraction in here between -1 and -2? What? Is that between -1 and -2? It's not there, is it? By the way, that tells you something. This is the list of all the possible rationals, and that's not in it. What does that tell me about this root then? It's going to be irrational. How about the one between -1 and 0? Is that in my list? Is there one up there that it could be? Now I'll pick your answer. What is between -1 and 0 would be -1/2. Now, by the way, if it's -1/2, if I am right, it has to be 2x plus 1. Now, this is the place where I gave you a hint on that last example. I'm not supposed to divide by that. So when I'm all done and I divide by this thing, I have to divide by 2 at the end to kind of fix that problem. Anytime you added a coefficient other than 1, we're going to have to divide it out to make it work. So I'm going to put -1/2 here. Now, what better happen right there? It better be 0. Now, I'm not going to go all the way to here because that already divided out perfectly. So let's see. I got a 2, I got a -1, I got a 0, I got a 0, I got a -4. But what did I tell you I had to do to these numbers because of the fact that I had a leading coefficient? I'm going to divide everything by 2. And so that's going to give me 1x squared plus no x's minus 2. Well, if you go back to what I said, is it's let's find all the real roots. Let's find them. So do you know what one of the real roots is? Where would this one hit 0? At 4. Where would this one hit 0? At -1/2. Here's the tricky part. Where does x squared minus 2 hit 0? So if you're asking where would this be 0, couldn't I move the 2 to the other side and say x squared is 2? So what would x be? Plus or minus square root of 2. So my 4 answers were 4, -1/2, and plus or minus root 2. Now look back at what it says. I saw that there should have been a root between -1 and -2 that didn't show up in my list. There was another one that didn't show up in my list that was between 1 and 2, correct? Why? Well, because those are irrational numbers. By the way, are they between 1 and 2? That kind of confirms what I was actually looking for. So here's what I want you to do. Can you guys take out a calculator? Go grab one. Let's see if we can figure out a little bit about where this works. We're going to find all of those roots, and we're going to develop some ideas here. Let's see, I'm going to go to here. I'm going to go to there. Here. All right. So you have a little polynomial, which is a 2x to the 4th minus 11x to the 3rd. So see if you guys can pop that in. Set a window, maybe -5 to 5. I think -5 to 5 should be sufficient. I'm making mine kind of match up with what you're probably going to be looking at. Now, my goal here, everybody, is to find the values that are between that where it hits 0. So let's take a look at what my possible values are. I don't know why this is actually doing that. Oh, that's going to work right here. Can you guys tell me what number goes into 15? What are all of the numbers that go into 15? It starts with 1. What's next? 3, 5, and 15. So that shouldn't be very hard. Now, what I always do is I write those, because remember, I'm going to take all of these numbers and I'm going to divide them by these numbers. But what are the only numbers that go into 2? 1 and 2. So, by the way, do you guys catch what I divided by? If I wrote the numbers down, then what did I show you is I was dividing by 1. What are the other numbers? Would be a half, 3 halves, 5 halves, and 15 halves. This time, notice none of them doubled up, did they? You know, before I didn't list the other ones because they were already in my list. So we took an infinity. We took an infinite number of options and we reduced it down to how many? 16. Which I look at that and I kind of hold my nose a little bit because I don't want to try 16 times. I like synthetic division, but not that much. I don't want to do all 16. Now, do you think Descartes had to do all 16? In fact, he did. He'd have to do a whole lot of them. So what we're going to do, though, is we're going to cheat ever so slightly, and we're going to look at what a graphing calculator shows us, or maybe what Desmos shows us. And let me see if I can make this thing do what I want it to do. Let's do a new share to my Desmos. This is what I see. Where does anything jump out at you right now about my story? Now, on a calculator, it's a little harder sometimes to do. I understand that. But do you notice anything really nice? Any really nice places you can tell that it happened? I see one at 3 itself. Now, what else do you see? I see one that's just a little bit to the left of -1. I see one a little bit to the right of the number 4. So let me look at this thing again. Do you see anything just to the right of 4? I do not. Do you see anything just to the left of -1? Again, I do not. What does that tell me about those two roots? They are irrational. What are the two roots that I'm actually going to check out? Is I'm going to try the number 3, and what other number am I going to try out? -1/2. Now, by the way, do you have the equation in your calculator right now? If you do, try this. Hit second calculate, which is the second trace button, and number 1 is value, okay? Can you hit that one? Ask it about what happens at, I believe it was -1/2. Just hit -1/2 and hit enter. What does your calculator do? What answer did it pop back at you? Did it pop back a 0 at you? Okay, Monster, you did? Yours did? So, by the way, is it worth dividing that then, if you already know the answer? I don't want to be hunting in the dark, so let's go ahead and do that. Now, I personally always like to divide larger numbers first, if I can. Now, I go pretty quickly through this because, honestly, multiplying and adding are one of the fastest things that we all know how to do, isn't it? I mean, those are the easiest operations you've been doing since you were pretty darn young. So, did that work? Did that show that the number 3 confirmed and it was, in fact, a perfect root? Looked pretty good to me. So, I now have an x minus 3. Now, was it -1/2 that you guys checked out? So can you help? What would I put over here to go with that root of -1/2? Which should be 2x plus 1. Now, if we have done it right, what better be the remainder right here when I'm all said and done? Is it better be 0? Now, please understand, I had a 4th degree. This is now a what degree? 3rd degree. I'm not ever going to get to this place because I've already divided it out. It's gone. I don't need to deal with it. But if we start going through this process, let's see if you guys can remember what the last thing is that I told you to be super duper careful about. I didn't divide correctly. What am I supposed to do if I ever have a coefficient? I have to divide it by that extra coefficient. So what does this 2 really mean? It was a 1 what? 1x squared. What's that? A -3x. And what's that? A -5. Now, personally, what I really like to do is when I do this dividing out. So you're going to see me do this a lot if you come up and ask me for help on a problem. See in this first step, look at that last coefficient. What is it? In this first step, it was x cubed minus 5x squared minus 13x minus 5. You know what? 3 doesn't go in anymore. What are the only numbers that go into 5? 1 and 5. You see that? So when we divide those things out, what you can do is you can start crossing them out because you would not be able to divide them again, and it would take the 16 options and make it smaller. So let's say you were working on your test and you didn't know, and you found one of them. Can you make your list go from 16 down to 8 pretty darn fast? Or sometimes from 50 down to like 6. That's really nice when that happens. Now, what do we do to get these last couple? Where are the last roots if somebody says, let's find all the real roots? I want all 4 of them. How are you guys going to solve that one? You have a couple of options. Does it factor? The answer is no, it can't, because we looked at our list. There's nothing in there in the list that works. How can you solve that? Go back in your days to Math 2 and Algebra 2. How can you solve a quadratic that is not factorable? Can we complete the square? We could, absolutely. What's the other option other than completing the square? Yeah. Which one do you guys like better? Do you guys like completing the square better when it's odd? You see that? When you cut in half and square, you're going to start getting a bunch of fractions. So what do you guys like better, the quadratic formula, or you like completing the square better? Let's go with the formula. So opposite b, plus or minus the square root. I hear people singing it. Minus 4ac. What's 4ac? Minus 4 times 1 times negative 5 is positive 20 all over 2a. By the way, what's the square root of 29 about? 5 point something, right? So what's 3 plus 5 point something? 8 point something divided by 2 is 4 point something. What did we see on the graph? Some 4 point something, right? What about 3 minus 5 point something? That's negative 2 point something divided by 2 is negative 1 point something. I mean, you can kind of see the remnants of what we found. Now, there's something extra that I have not gotten to yet that I've been trying to figure out how I was going to introduce this, because I don't normally like to introduce it the way I am today, because I like to give you a little bit at a time, but we're jumping right into a block day and all of that kind of stuff. So it's hard to do this in a gentle way, but I feel like I've got to show you a little something that's kind of interesting. So I'm going to go with one that I think is not going to be particularly nasty, but actually, yeah, this is going to be fine. Okay, so let's just say, for the sake of argument, that you ask the question, I think 3 could be a root. Now, so far, I think everybody in this room knows something. Could 3 be a root of this problem right now? No, that would be absolutely stupid. Why? Because 3 is not a factor of 5. So, I mean, you know this is already just a bad number. I'm trying to give you something that is gentle and nice and easy. So I just wanted to let you see a principle, because there is a little helper that's really, really cool that if you have never seen it before, it's worth seeing. And it's right here. Now, I want you to think about something. And I don't really think this is even in your textbook. They have it written down in a slightly different way, and I think this is more powerful. So did 3 work? But there's something that's kind of interesting. Look at all of these coefficients that are down across the bottom. What do you notice about all of them is that they're all positives, aren't they? So what would happen if, just for fun, I'm like, well, 3 failed, maybe 4 will work? I want you to think about that. I know 3 failed. Would 4 work, or maybe 5? And I want you to think about what would happen if I took this number and I made it go bigger. What would happen if I made that bigger? What would happen? This would stay the same. What would happen to this number? It would get bigger, wouldn't it? What would happen to that number then? It would get even bigger. And then that number would get even bigger. And then this number would be bigger. Is that ever going to get me anywhere good? So could 5 be a root? Well, you look right here and you're like, yeah, it could be. But could 5 be a root? No, because the reality is, as soon as they are all positive, don't keep getting bigger, because what are you trying to get to is the number what? I'm trying to get to 0. So as soon as they go all positive, where does the answer have to be? It has to be smaller. So what we're going to call this thing is an upper bound. And so that actually takes me back to this thing right here. An upper bound for a polynomial is a value for which all remainders are non-negative. Now, I mentioned positive a second ago, but 0 would do the same thing. I'm looking for 0 in the final answer. So as we go through all that, we want to make sure that we just, if they go pluses and minuses, it's possible that something good can happen. Well, it turns out there's another way to do that, and it has to do with, remember odds and evens from when we did something before? Like one of the first units. Remember how f of negative x is negative f of x in an odd function? We could plug that in. Turns out the upper bound, if you look for where the signs are all the same sign, all positives or zeros, the lower bound, it's a value for which all remainders alternate signs. So as soon as they start going plus minus, plus minus, plus minus, if you get bigger, those plus and minuses are just going to just amplify even more and go a little bit out of control. So one of the things that I like to do, and you will see that in some of the worksheets and things that I will give you, is I will give you a chart that looks like this. So I know that feels a little bit awkward when you first look at it. It looks a little bit overwhelming, and I'll try to get a copy of this up online for those of you guys that aren't here. But really, it's not about the specific numbers. It's more about the discussion. So what I just did is these are synthetic divisions. So I know the first time you see that, it just looks like a big blob of a bunch of numbers. But look how synthetic works. I drop the 4. What is negative 5 times 4? Negative 20. Add that to 16, you get negative 4. Negative 5 times negative 4 is 20. Add that to negative 13, and you get 7. So what you're going to see right here is all of the remainders in synthetic division. What I didn't show you is all the work. I made a little Excel spreadsheet to do this stuff, and I just had it give me all the answers, and it didn't show the little process in the middle. It's actually very simple to do. But can you guys tell me, find out where all of the numbers went straight positive? Can you see the first number that does that? Does 3 do that? So is the number 3 an upper bound? By the way, is the number 4 an upper bound? So if you're finding the upper bound, do you guys like 4 better, or do you like 3 better? Okay, remember, what's our goal? Our goal is to find all the zeros, right? To find all those roots. That's kind of the whole goal of everything that we're doing. So whereas 4 is a good thing to say, hey, make sure you pick all your numbers less than 4, isn't saying pick it less than 3 even better? So this is kind of funny. This is called the least upper bound. So I liked 4 just fine, but I like 3 better because I wanted the lowest one that I could out of the list to narrow it down. Okay, what else do you guys see? Do you see any of them that alternate signs, pluses and minuses? I see plus, minus, plus, minus, plus. So you see this guy? That is a lower bound. If I tried to make negative 6, these numbers would just become even more radically oppositing all the way through. And so this is an upper, this is a lower bound. By the way, is negative 4 also a lower bound? Now, as I go through this, one thing I have to be super careful about is the language is super technical. This is non-positive, isn't it? I mean, sorry, this is non-negative. I hate saying it this way. Would you guys buy this as non-negative? Is this non-positive? I know you want to say positive, negative, positive, negative, positive. That's what you want to do, but 0 counts like a wild card. And that's kind of the way you have to look at it. If you have a positive, the next one should be negative, but if it had been 4, 0, 7, it still would be a lower bound. So when I look at it, is it positive or 0? Yes. Is it negative or 0? Yes. Is it positive or 0? No. Did it alternate? No. So what would that tell me is that if you looked at this big nasty thing, where are all of the roots? They're somewhere between -5 and +3. So when you look at your big fatty little list of all of the things that you could have, because this thing could go all the way up to 50. And 1, 2, and 4 are my possible denominators. So you tell me, could 10 be a root? Can 10 be a root? No, it can't be. Because what do you know about all the roots? They have to be underneath the number 3. Okay? Could 5/2 be a root? 5/2 is a legit player, isn't it? Now, do you see how very quickly, if you could narrow down your list, this would help? Because it's kind of painful to do all this. But let's look one more time. Because I got to make such big bang for every single buck that I give you guys. Last time when we were together, I showed you something, and I only showed you one of them, and I felt kind of bad about showing you one and calling it a day. But that was that when we had this problem right here, we found out that if I plugged 2 into the original, I got -6. So I know that feels a little bit awkward. This is from earlier in the day. I did a synthetic division on the number 2. I got a remainder of -6. So here's the thing that's really, really cool about that. And I'm almost done with what I was going to give you today. And then I'm going to give you some time to work. Your goal is to get 0. But here's the coolest thing. When you divide, whatever this is not just wasted. Back in elementary school, remember when you did long division and you tried something, oh, and it was too big? It was kind of wasted effort, but not totally, because what did you always know? That it had to be a number smaller, right? These are not wasted because what I'm looking to see, did 2 work? The answer is no, because it's not at 0. Where is it? It's at -6. It's a little too low, isn't it? So watch how this works. This is kind of cool because this is called, again, the remainder theorem. If I plug -1 in to the thing, I tried to divide it, what showed up right here is the number 35. Guys, that tells me this is a coordinate -1, 35. Do you see that? Well, check this out. Look right in here. What just happened? The graph was sitting at 35, and by the time it hit 0, it's at -50. What did it have to pass through to go from a height of 30 to a height of -50? It had to do 1. So where did that happen? It happened somewhere between -1 and 0. You follow me? So somewhere between -1 and 0, there had to have been a root. Can you guys find another one that you can see where there had to be a root? Somewhere between 2 and 3. You see how it went from negative to positive right in there? Somewhere between 2 and 3. Now, by the way, go back and look at the list. Is there a number in my list that seems legitimate that I could try between 2 and 3? Look at my list of all of the possible rational roots. Can you see a fraction in there that's between 2 and 3? 5/2. So should we try 5/2 if we were going to do that? I'm not going to right now. Understand that, please. But should I try 5/2? Absolutely. Now, is there a number in my list that makes sense to try between -1 and 0? This is a little harder. Is there one in between -1 and 0 that we might want to try? Is -1/2 in my list? Because remember, these are the numerators, those are the denominators, so negative a half is a possibility, isn't it? What's the other one? Is negative quarter also a possibility in my list? So when you think about the infinite number of answers, we took infinity and we divided it down to 1, 2, 3, 4, 5, well, 15, well, shoot. We've got 15 fractions sitting right here. You guys see that? I got 15 fractions, so there's actually 30. So I took infinity and I cut it down to 30. Cool? But then out of that 30, I cut it down to here, and what did we cut it down to? 1. Wasn't there only one legitimate possibility in this entire list that actually fit inside there? And then how many chances did we have right here? We only had 2. And so as you guys go through this work, the way I work on this is, do you guys already know how to solve quadratics? So what I do is I use the big guns. I do these kind of fancy techniques until I get it down to a quadratic, which means on the test, if I give you a cubic, what power am I handing you? A cubic is 3. So what do you have to find to get it down to a quadratic? 1. If you can find 1, then you can get out of jail using the quadratic formula or simple factoring techniques. If it's a 4th degree, how many do you got to earn? You got to earn 2 of them, and then you can get out of jail on the other parts. Okay, you follow me? So in a nutshell, there's a couple things that I wanted to go over with you today and make sure you got it. Number 1 is if you do synthetic division, what is the answer is actually a coordinate. So where is this graph if I plugged in -4? If I went and I actually studied the graph, where would the graph be? It was at 182. You see that? That's one thing. That's called the remainder theorem. If you do synthetic division, whatever's left over is an actual coordinate, which is cool. Number 2, why did we circle the number 3 as a significant value? Because we called that an upper bound, which means if you're looking for the zeros, don't go up anymore because there's nothing that's going to be good that goes above that. Fair so far? Why did we circle -5? Because that was a lower bound. So basically we're saying, hey, I've got an upper bound, I got a lower bound, look in here. Why would I do that? Because I'm trying to narrow my search. Then we also had our rational zeros theorem to kind of narrow it even further. The last thing that I never mentioned to you guys is this thing right here. And I'll probably put it in your notes tomorrow. Why did we highlight this chunk and this chunk? Because there had to be a root in there because it went from negative to positive, didn't it? And we know polynomials are smooth and continuous. They're nice graphs, so it can't go from positive to negative unless it actually crossed through the axis, right? Well, we have a fancy word for that in math. We have a little bit of a fancy word, and that phrase is called the intermediate value theorem. Guys, when you're driving from here up into the mountains, what's the elevation of Red Bluff? Elevation of Red Bluff is, it's honestly about 100 feet, somewhere around 100 feet. I mean, we are really, really picking low, okay? Elevation of Mineral, isn't it somewhere at 4,000? Did you have to pass through 3,000 foot elevation to go from here to there? Why? Because that's an intermediate value. To go from 100 to 4,000, did I have to go through 3,000? Now, could I have maybe drawn over that several times on the way because you go up and over a pass and you do, but it's going to happen at least one place, doesn't it? So the intermediate value theorem says if you go from one number to another, you have to cross through how many numbers is every picking one of them in the middle, don't you? At least once. It might be more than once. By the way, could you go from 100 feet to 5,000 feet and pass through 6,000 feet on the way? Could you do that? Could you maybe go up and over and then come back down? Oh, we do that all the time. You guys ever been to Ashland? You have to go up a big fat hill before you drive down this hill into Ashland. Sometimes you go higher. The intermediate value theorem doesn't say those are the only numbers, but it guarantees those values. So usually we talk about the intermediate value theorem, though, specifically saying if you ever go from a positive to a negative, what did you have to cross through? You had to hit 0. And if you ever went from a negative to a positive, you also have to go through 0. Technically, it's more than that, but that's really what we care about, because in math, generally, we just want to find zeros. That's just kind of what we do. So your homework right now is the following. We're in 2.4. Now that's 2.4 is in your textbook. And your textbook is still posted in Google Classroom. I haven't used it in a little while. I really honestly thought about retyping it and all that kind of stuff, but honestly, it was hours of my world and it really was not that big of a deal. So I want you to do this series of questions. And I generally was trying to get multiples of 3 because then you could check some of your answers, but then be honest on some of your others, evens and odds, because answers are in the back of the book. But unfortunately, there was a place where they said, are they roots? And as it turns out, all of the ones that were multiples of 3 were no, 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 no. And I'm like, oh. So that's why I broke my pattern in here a little bit in the middle so that one of the answers actually didn't actually match all of the others, because really I want you to see both things that could happen, okay? So the rest of the period, which I know is not a whole lot of time, it's about 15 minutes. Can you guys go into Google Classroom, find chapter 2, section 4, and go through a couple of these problems? And we're going to do a lot more of that tomorrow. Tomorrow will be largely a work day. I do have some notes that I'm going to cover with you guys, but then it's going to be some work time. And so that's kind of where I'm going to end it today. So you guys online, if you want to hang out with us, you can. If you want to check out, that's all right. So you're good to go. And I'm going to go ahead and hit the